Okay, welcome back. This is 3.1. Actually attacking one of the two main problems here in calculus, the tangent line problem and the area problem are the two main problems. In the beginning, we just worry about the tangent line problem. So this is called the derivative. But it's really just slope. It's a variable slope. So the idea is that for a given line, there is a constant rate of change, right? There's something called a slope. So I know this guy is positive everywhere. The slope is greater than 0. This particular line, its slope is negative. And then this line here, its slope is 0. And then we have this vertical case where the slope is undefined. Okay? Okay. So given a function, we want to take this idea and attach it to the function, right? So we have now these curvy guys that we can include, and we'll be looking for the slope at any particular given value of x. So take x to be right there. And we'll want to know the slope of the tangent line to the curve at that point. Okay, so a tangent line is a line that just barely touches the curve. And here, at this point, the slope is negative, right? Okay, so we'll want to know if the slope's negative or positive. And we can actually attach or figure out the value of the slope of the tangent line at these points. Okay? So it's basically just slope, but now we have more complicated functions, so we'll want to know the slope at various points on the curve. Okay? We'll want to describe this type of thing with slope values. Okay, that's the idea. I want to take what I learned about slope and now apply it to more complicated functions. Okay, so how do I do that? It's going to be from limiting secant lines, taking a limit of a bunch of secant lines to a curve as the points get closer and closer to each other. So what does that look like? Let's draw a picture here. And we have a nice curvy type function like this. And let's say that I am really worried about what the slope is, maybe at this point C. Okay. Well, in the beginning, I'm going to approximate that by looking at some value out here. So C plus some delta x, okay, some change in x value. Okay, so I can get an approximation to the slope by figuring out the slope of this secant line. Okay, so to figure out the slope of that secant line, well, how do I do that? Well, it's just figuring out the slope from the slope formula, right? The slope of the secant line is just going to be y2 minus y1. So y2, f of x plus change in x. Oops, this should be c, sorry. I'm ahead of myself. F of c, let me rewrite this. So the slope of the secant line is f of c plus change in x minus f of c, y2 minus y1 all over x2. So it'd be the c plus change in x minus c. And then, of course, what does that equal? That just equals f of c plus change in x minus f of c all over, well, the c's cancel, so we just get a change in x in the denominator. Okay. Okay. So the calculus part is we can take the limit as these change in x values go to 0. Okay, so I'll write it backwards. We have change in x going to 0 will allow us to kind of figure out the slope of the tangent line to this curve. So what we're super duper interested in would be the slope of this line, right? And we haven't found that. We found the slope of the secant line, but if we keep taking points closer and closer to the C value, what we'll get is a sequence of slopes of secant lines. Okay, so there'll be one there, and then we'll get one here, and then we'll get one here. And you see the slopes of these secant lines are getting closer and closer to the slope of this blue line, which is what we want. And that's a limiting process. So if we take the limit of this thing, and this thing we call the difference quotient. This guy right here is called the difference quotient. Okay. If we take the limit of these difference quotients as change in x goes to 0, we should hopefully converge to a limit that gives us the slope of the tangent line at this value that we care about. Okay, so let's look at that process. How does that look? We'll write it. We want the slope of the tangent line at C. So we take the limit of the difference quotient as change in x goes to 0. Okay. And so what does that look like? It'll be the limit as change in x goes to 0 of f of c plus change in x minus f of c all over change in x. Okay. But really all this is, I mean, it's just a slope formula, right? It's y2 minus y1 over x2 minus x1. It's nothing to be intimidated about. It's slope from basic algebra. Okay, okay, so if this thing exists, we'll say that the line, if the limit of the difference quotient equals some number m, then the line passing through c comma f of c with slope m is the tangent line to the graph of f at the point c comma f of c. Just trying to touch base with the book, basically, is what I'm trying to fit this to what the book is saying. Okay, so with slope m is the tangent line to the graph of f at the point c comma f of c. Okay, very good. So I just want to make sure I'm touching base with that. Let's look at some homework problems then. This will be number 5. Find the slope of the tangent line to the graph of the function at the given point. So find basically slope at point. And they give us a function. So it'll be f of x equals 3 minus 5x. And then the point is negative 1/8. So your answer is there, right? If you remember y equals mx plus b form, the answer is negative 5, right? The slope of a line is a constant rate of change. A linear function has a constant rate of change, so it's negative 5. It's sitting there in the formula. No matter where you are on the line, it's always the same. Okay, but we should be able to verify this using our new high-powered limit formula for this thing. So we'll take the limit as change in x goes to 0 of, what was the formula? F of, this time we want c, and this is our c value here is negative 1. Okay, f of c plus change in x minus f of c all over change in x. Okay. All right, so this will equal the limit as change in x goes to 0 of, and I want to plug this into this guy here. So I have 3 minus 5 times -1 plus change in x, and then minus f of -1, so that would be 3 minus 5 times -1. Sorry, I'm going off the page there. All over change in x. So I'm just plugging in the appropriate values into this function. And then that'll equal the limit as change in x goes to 0 of 3. I have to distribute the minus 5, so I'll have plus 5 minus 5 change in x, and then minus 3 plus 5, which is 8, all over change in x. Okay, so this will be the limit as change in x goes to 0 of, well, 3 plus 5 is 8, minus 8 is 0, so I just got minus 5 change in x, all over change in x. And then you can divide out the change in x's, so long as change in x is not 0, and for limits, we don't care about exactly at 0, just the approach, right? So it's kind of like a removable discontinuity situation. We got the change in x going to 0 of -5, and the limit of a constant is just a constant, right? So that would equal -5, okay? Which is what we want, what we expected. The slope is -5, so now we have this high-powered tool to figure out the kind of slope at a point. Let's apply it to now a non-linear function, in particular the first easiest kind of function you always encounter, a parabola, right? Right, so this guy is shifted down or shifted up by 5. 1, 2, 3, 4, 5, and it will go down like this. Just getting a picture, and then at 3, 4, 1, 2, 3, -4 is down here. We would expect that the slope of the tangent line to this curve is kind of negative, and it's also big, right? So it'd be like negative, I don't know, 10 and then over 1. So -10 maybe the slope is, I don't know. But anyways, we should get a negative value coming out of our limit. So let's go at it. Limit as change in x goes to 0 of f of, and this time the c value is right here. We want to know the slope at 3. Okay, so f of 3 plus change in x minus f of 3 all over change in x. Plug this material into this guy. So f of 3 plus change in x means replace in this formula x, wherever you see it, with 3 plus change in x. Okay, so that's what I'll do. So in this formula, I'm going to write 5 minus, instead of x, I write 3 plus change in x, and then that's squared. Okay, so that's just this portion, is this portion. And then I minus away f of 3. So I plug 3 into this formula now. And make sure you put it all in parentheses. So 5 minus 3 squared is 9. And that's all over change in x. Okay. So this will equal the limit as change in x goes to 0 of 5 minus, I got a FOIL, so 9 plus 3 change in x plus 3 change in x is 6 change in x, plus change in x squared, and then minus 5 minus 9 is -4, so that would be plus 4, all over change in x. Right? I need to distribute this negative all the way through, so I got the limit as change in x goes to 0 of 5 minus 9 minus 6 change in x minus change in x squared plus 4 all over change in x. Okay. So that'll equal the limit as change in x goes to 0 of 5 minus 9 is -4, plus 4 is 0, so that the constant terms all go away, and I just have -6 change in x minus change in x squared all over change in x. And we were expecting the limit to be negative, and it looks like it's probably going to be that way. Let's look at this. So to figure out this limit, it's, currently it's a 0 over 0 form. It's indeterminate. So we have to use some algebra to clean it up. In other words, factor the change in x out of the numerator. So we get a change in x times -6 minus change in x all over change in x. And then you see, okay, I can remove those and get rid of the 0 over 0 form. And now it's just a substitution limit. So it'll be -6 minus change in x. And finally, if you plug in 0 for change in x, you just get -6. Okay. So down 6 over 1. It's kind of what we expected. I think I said -10, right? I did overkill. Okay. Okay, great. Now we want to make this a little more flexible. So instead of just requiring the slope at a given point, we want the slope for any given point. Okay, so we want our limit to result in a variable expression if that's what's required. Obviously, the slope for linear function is always going to be the same. You're always going to get out -5. But for something like this, the slope is variable. Okay, so we want a formula that kind of gets out of always having to submit your particular point. Okay, we want a variable formula. So what we're going to end up doing is just putting x in place of c, and that will give us the derivative formula. Okay, so section 2, now officially the derivative of a function. Okay, and we have the definition of the derivative. And so it'll be just like the limit we saw before, but with the x instead of c. So the derivative of f at x is going to be the limit of the difference quotient, f of x plus change in x minus f of x all over change in x as change in x goes to 0, provided that this thing exists. And we're going to have some new notation here. It'll look like this, f prime of x, provided the limit actually exists. And we'll look at some cases where the thing doesn't have a derivative here in a bit. So the other type of notations for the derivative, of course, we just gave you that one, f prime of x, what's called the Leibniz notation, dy over dx. So this tells you that it's the derivative of y and then which variable you're taking the derivative with respect to. So eventually we'll do multivariable expressions when you're dealing with 3 dimensions and 4 dimensions and stuff like that. And you'll need to tell us which variable is the one you're taking the derivative with respect to. Okay? Other notations, y prime. So instead of f of x, you have a y, so you go y prime. This other one, the derivative with respect to x of f of x, and then stuff like you would see in differential equations, dx of y. So the main ones that we use are these guys right here. Oops. There's also in physics, they sometimes use dot notation, so sometimes I've seen it like this. Okay. Anyways, let's actually now find the derivative using the limit definition. And 21 is the question. So we want to find the derivative of this ugly looking critter, 1 all over x minus 1. And what it'll do is give you a formula such that if you want to know the slope at a particular x, all you got to do is plug it into that formula, the derivative formula. Okay? Okay, so how is this going to work? We want the limit as change in x goes to 0 of f of x plus change in x minus f of x all over change in x. Right? So first I'm going to plug this x plus change in x into this thing here. So I have 1 all over instead of x. You now have x plus change in x minus 1. Then minus f of x, which is 1 over x minus 1. I'm going to find a common denominator. So this denominator needs an x plus change in x minus 1 in top and bottom. And then this denominator needs an x minus 1 in top and bottom. So the numerator from this guy will be x minus 1, and then I'm going to subtract the numerator of this guy, which would be minus x plus change in x minus 1, all over the common denominator of x minus 1 times x plus change in x minus 1. And then dividing by change in x is the same as multiplying by its reciprocal. So that's the same as multiplying by 1 over change in x. Okay, so I need to distribute this and then combine like terms. Let's see. I have this equaling the limit as change in x goes to 0 of x minus 1 minus x minus change in x plus 1 all over, well, we have another change in x now, change in x times x minus 1 times x plus change in x minus 1. Keep on simplifying until you feel like you can't go any further. X minus x is 0, 1 minus 1 is 0, so we'll have a negative change in x all over change in x times x minus 1 times x plus change in x minus 1. You could check the form. You can't do a substitution yet, right? So you put in 0 for change in x, you get 0 over 0. So you need to remove common factors, and then you'll be good to go. So this will equal the limit as change in x goes to 0 of negative 1 all over x minus 1 times x plus change in x minus 1, smushing that in there. And if you do a substitution, things work out, right? So you'd end up with your derivative negative 1 all over x minus 1 times x minus 1, which will be x minus 1 squared. Okay? And that's your derivative. That's f prime of x. Okay, so those will give you a lot of practice with just manipulating symbols and doing some algebra. We want to talk now about the failure of differentiability, and we'll want a different form for the derivative in order to pull this off. You'll see the different forms of the derivatives are all have that kind of slopey feeling to them. So anyways, differentiability, and we also want to consider the connection to continuity, differentiability. So if something is continuous, does that mean it's differentiable? If something is differentiable, does that mean it's continuous? Is there any connection that you can make? That sort of idea. And then we also want to worry about failure of differentiability. And that will just be the failure of the limit of the difference quotient. So it'll be the same kinds of failures that you saw when we dealt with failures of limits, because the derivative is essentially just a limit. Okay, so first we need an alternative form for the derivative. Okay, so if we start with our other form, f prime of x, and sometimes they write it the limit as change in x goes to 0, change in y over change in x is another way to write it. But the way we've been playing around with it, it looks like this. change in x. Okay. So if you do a substitution, you'll get kind of what we're after. Okay. So if you we, in particular, the book is going to want to work with f prime of c and then develop the formula from there. But I believe you could easily do a nice substitution on this guy and get another formula. I guess I have to work with this one though, okay, just to be consistent with the book. So this guy, originally we had it, this was the first definition we worked with, it's the non-variable type. So you have to be supplied with a particular point at which you want to know the slope of the tangent line. So this would be f of c plus change in x minus f of c all over change in x. And what we're going to do is a substitution. We're going to say let change in x equal x minus c. Okay? Okay, so not much is going to change wherever you see, but wherever you see change in x, put x minus c instead. So x minus c is going to 0. And then in here we'll have f of c plus change in x, which is now x minus c, minus f of c all over change in x, which is x minus c. So the limit as x minus c goes to 0 is equivalent to saying the limit as x goes to c. All right. And you probably have to go back to the definition to clearly see that, but I think intuitively you kind of say that those guys are equivalent. You know, this is just saying the distance between x and c is 0. This is saying x actually equals c, which in that case the difference between x minus c would be 0. Okay. So I think intuitively that's obvious, but if you really super duper want to be careful, you'd have to go back to the strict definition. Anyways, simplifying here, c minus c is 0, so I have f of x minus f of c, and then all over x minus c. So we get a different form, but it still has that slopiness quality to it, right? So it's like f y2 minus y1 over x2 minus x1. Okay. Anyways, let's sort of dive in there. And the first objective here is the continuity issue. So we want to know basically the connection between continuity and differentiability. And the theorem says that if something is differentiable, then it's continuous, but not necessarily vice versa, right? So the idea, this is a logical statement, and you can't necessarily flip it, right? I think that's the converse error. You can't say the converse is true. It's kind of like if I hit a home run, no, if I hit the ball out past the fence, I get a home run. But you can't necessarily say if I got a home run, then I must have hit the ball out beyond the fence, because some people get in the park home runs and that sort of thing. Okay, so you can't basically just say if continuous, then differentiable. That won't work. If you want equivalent logical statement, you got to take the contrapositive, which will look like this. You negate both and then flip the direction of the implications. So that will say if it's not continuous, then it's not differentiable. Okay. But that's all you can get from logic. Okay. You really can't get much more. So this is called the contrapositive of this statement. Okay. In logic symbols, when you're given a statement P then Q, the logical equivalence statement is the contrapositive, which is not Q, implies not P. It looks like that if you take some fancy logic class. Okay, so anyways, we want to prove this, and to prove it, we're going to use this definition. And we also need one other fact, that is, if you have kind of the limit. So this is kind of just a fact which you could prove, but you'd need to go back to the strict definitions. The limit as x approaches c of f of x minus f of c equaling 0 implies that the limit as x goes to c of f of x equals f of c. Okay? And I think it's, again, it's kind of an intuitive thing. You would think that, oh, I just have to add f of c to this side, and I would get this statement. And if you go back and prove it, that turns out to be entirely the case. Okay, so you can do this. So this is just a fact or a little lemma that you could use to get to our conclusion that if it's differentiable, then it's continuous. Okay, so our proof then looks like this. We'll suppose a function is differentiable. So suppose f is differentiable at some point c. Okay, then we note the limit of f of x minus f of c as x approaches c. Okay. So what is this? Well, we can finagle the definition of the derivative by multiplying in x minus c over x minus c. Okay. So this will be equivalent to f of x minus f of c all over x minus c times x minus c. And so you see these x minus c's would cancel out, and you would get right back to this original statement. But the important bit is that you've created here the derivative, and we know the derivative exists, so I can figure out this limit. The limit of x minus c is just 0, so I can figure out this limit as well. The limit of a linear function, you can figure that out by doing a substitution because this thing's continuous, right? So the limit of the product then will be the product of the limits, and so I'll have the limit of f of x minus f of c. I'm really going to have to smush this in, all over x minus c times the limit of x minus c. Okay. And what is that then? That's equal to f prime of c times, if you do a substitution for x minus c, let me write that out just so you can see it. This portion here will be 0. If I plug c in for x, I get c minus c, which is 0. So this will be equal to f prime of c, which I know exists because that's my supposition. Suppose f is differentiable. And then times 0, which equals 0. And then by the fact, if you have the limit of the difference of these two guys equaling 0, you know the limit of f of x is equal to f of c. And then by the definition, the criteria for continuity, we have it. I mean, that's basically says that this thing is continuous at c. Okay? So hence, it is continuous. Differentiability implies continuity. Okay, so that's an important kind of theoretical detail that will pop up every once in a while, and you're going to get more and more proofs as you go through the book. Calc 2 has tons and tons of proofs, but we're going to see more and more proofs as well. We'll have like, what do we have? The Rolle's theorem, mean value theorem. All these fundamental theorems of calculus will be rolling in eventually, and you want to get a little more practice in reading proofs. Just going through, if that's the kind of direction you want to go in your career. Okay, so anyways, let's now look at failure of differentiability. It's part B, I guess. Failure of derivatives. And it's basically just going to be wherever the limit of the difference quotient fails. And limits fail in 3 different ways. You can have different left and right hand behavior. You can have unbounded behavior. And you can have oscillating behavior. We'll only look at the 2 types, the left and right hand behavior, and then the unbounded behavior. So anyways, let's look at some examples, right? So example let f of x be a piecewise function, we'll say -1 if x is less than 0, and then +1 if x is greater than or equal to 0. Okay. We're concerned about the derivative at x equals 0. Is it differentiable? Okay, so one thing you could do is look at the different right and left-hand derivatives, right? So we'll use the second form of the derivative that I introduced. And we're looking as x goes to 0, and we'll consider from the left. So that'll be f of x minus f of 0 all over x minus 0. Okay. If we evaluate then, limit as x goes to 0 from the left, we have f of x. F of 0, go back to the piecewise function, that'll be 1. So f of x minus 1 all over x minus 0 is x. We're approaching from left. We could do a little analysis table here, a numerical analysis kind of deal. So negative 0.1, negative 0.01. And what are we dealing with? Well, at negative 0.1, we'll have -1, and then -1 all over whatever the heck x is, negative 0.1. So -1 minus 1 all over negative 0.1. Okay, so this will equal negative 2 all over negative 1/10, which is positive 20. This guy then is negative 1 over negative 1 over negative 0.01. So that would just be negative 2 over negative 1/100th, which will give me 200. So I think it's going to go 20, 200, 2,000. We say it's going to infinity. All right, that's already telling me this thing is not going to be differentiable. It has this unbounded behavior. Okay. And I believe the book will consider this vertical tangent line in that direction, but I'm not entirely sure about that, so I'm going to leave it at that. Let's just look at the other direction. So the limit as x goes to 0 from the right, we have f of x, again, minus f of 0 all over x minus 0. So that will give me the limit as x goes to 0 from the right of f of x minus 1 all over x. And then again, you could do in our table. So I have x's and y's. Coming in from the right, I'll have 0.1. So the big difference is now this is going to end up being, well, is that even true? Let me not jump the gun here. So f of x, I have to be a little bit careful because now I'm coming in from the different directions. So f of anything greater than 0 will just be positive 1. Yeah, so this is a little different. So this would be 1 minus 1 over 0.1. And then in particular, that's just 0 over 0.1, which is, of course, just 0. So it looks like in this case, all of your values are going to end up being 0. This will be 1 minus 1 over 0.01, which will be 0 over 0.01, which, of course, then is 0 again. Okay, yeah, so this one is going to 0 from that direction. Okay, but ultimately, is the thing differentiable at x equals 0? No. Okay. It has a right derivative of 0, but the left derivative is different. Okay. You need both these derivatives to be the same for the thing to be differentiable. Okay. And not only that, you need them to be some number. Okay. If it's going to infinity, that would, in my opinion, that would indicate it has a vertical tangent right there. Okay. but I would consult a book to be 100% sure on what's going on there. All right, let's look at another one. So this is 81. We have f of x equals the absolute value of x minus 5. And if you've forgotten how that works, the piecewise version, negative x minus 5 if x minus 5 is less than 0. In other words, if x is less than 5. And then it's positive x minus 5 if x minus 5 is greater than or equal to 0. In other words, if x is greater than or equal to 5. Okay. So again, we'll consider the left and right limits. The limit from the left, and again, we have f of x minus f of 5 all over x minus 5. Okay. So here we go. This is equal to then the limit as x goes to 5 from the left. If the values are less than 5, we're using this function for f of x, so it would be negative x minus 5 minus f of 5. So when x is equal to 5, we're on this piece of the function. 5 minus 5 is 0, so I would have 0 all over x minus 5. Okay. And then if you were to simplify that, limit as x goes to 5 from the left of negative x minus 5 over x minus 5, that's just going to be equal to negative 1. Let's look at the limit from the other direction. So I have f of x minus f of 5 over x minus 5. It's the same kind of idea, except now we're using the other piece of the function. Okay, so my values are greater than 5, so I'll be on this side, and x minus 5 will be f of x. F of 5, again, is 0. So I have x minus 5 over x minus 5. That's just equal to the limit of 1, which is 1. Okay. In other words, the limits are not the same, so this derivative will not exist, okay, in this particular case. If we look at the graph of the function, what do we have? Well, we have shifted version 1, 2, 3, 4, 5 of the absolute value function, which looks like this. And we note the thing is continuous, but it's not differentiable. Okay, so continuity does not necessarily imply differentiability, but differentiability does imply continuity. Okay? So here we have an example of something that's not continuous, but is differentiable. Or sorry, but it's not differentiable, but is continuous. Or maybe we should say, is continuous, but not differentiable. Okay. Let's look at one more where we have a vertical tangent line type issue going on. So in particular, let's say, does f of x have a derivative from the right at x equals 0, and I want to try f of x equaling the ln of x, right? So clearly this thing, whatever the heck is happening there, the tangent lines, if you look at them, they're getting more and more steep, okay? So I would say the slope of the tangent line at x equals 0, I mean, it's not even defined at 0, right? I don't know. I just want to take a look at that. Maybe that'll cause some gears in my brain to move somehow. Okay, so let's take a look at it. I'll use the definition, the second definition of the derivative. I want to go x goes to 0 from the right of this thing. So I'll have the ln of x minus, and already I have an issue, right? Because I can't figure out f of 0 it's not defined here. So this thing is going to fail miserably. It's definitely not differentiable, I would say, in my book. Let's look at a different one then. That was kind of a pathetic example. How about f of x equaling the square root of x minus 1 at x equals 1. So the graph of this thing, let's take a look at it. The square root function, of course, looks like this. This is shifted over by 1, so it looks like this. And then the slopes, you know, as we approach 1, again, it kind of looks like they're getting more and more steep, just like up here. But this function is different than this function, because this function is actually defined at x equals 1, right? It's 0. The square root of 1 minus 1 is square root of 0, which is just 0. This guy wasn't. You know, the f of 0, I have no idea. It's not defined. So let's see what happens this time. So the limit as x goes to 1 from the right of this thing, we'll have f of x, which is the square root of x minus 1 minus f of 1, which will be 0, all over x minus 0, or x minus 1, sorry. Okay. So what is this? This is equal to the limit of the square root of x minus 1 all over x minus 1 as x goes to 1 from the right. I can simplify that. So that would be the limit as x goes to 1 from the right, noting that the exponent on this is 1, the exponent on this is 1/2. So it would just be 1 all over the square root of x minus 1. And then this guy is, if you do a substitution, it's L over 0. So we know it's either positive or negative infinity. In other words, it's not going to be differentiable, but let's just see where it goes. So I'm coming from 1 to 1 from the right, x and y values here. 1.1, so it's a positive over a positive. It's going to positive infinity. Okay? And I believe the book will define that to be a vertical tangent line. When it goes off to infinity like that. So I was wondering if there was a vertical tangent line here, but there's not, because the ln function is not even defined at 0. But here in this case, you have a slope that's getting steeper and steeper and steeper. The function is defined at 0, and but yeah, the tangent it's a vertical tangent line, right? So it's like you have a undefined slope, I guess. Okay. But, you know, go look in the book to be 100% sure. That's what I'm going to do before I give my lecture in class. And, okay, thanks for watching.